In this lecture, we'll have a look at the linear regression model when you log one or more of your x variables. So to consider a simple example, let's say that yi is beta 1 plus beta 2 and we do log of xi plus an error term. This model is linear in parameters, but it's non-linear in data. That means that beta 2 cannot be interpreted as the unit increase in y when x increases by 1 unit, the way we typically interpret a linear regression model that's linear in data. Instead, the correct interpretation is as follows. Beta 2 divided by 100 measures the unit increase in y when x increases by 1%. So for a concrete example, let's consider this data set, final result on a final exam, the SATV score, SATM score, and the GPA score. So let's try to explain the final result with the log of SATM. So you would just do model ordinary least squares. You would do the final, and let's explain it with just the log of SATM. You can create that by just clicking this plus button. Okay, and the estimated parameter is 30.82 something. So the interpretation of this result is then as follows. If this SAT math score increases by 1%, then the result on the final exam can be expected to increase by 0.3, 30 divided by 100. So let's see how that follows from this model. The percentage change in x is delta x over x, and the unit change in y is delta y. So if I take the ratio of these, delta y divided by delta x over x, that becomes delta y over delta x times x. And this is approximately equal to dy dx times x. That's in generic notation. If we calculate dy dx when y is just beta 1 plus beta 2 log of x, then we see that dy dx is beta 2. Derivative of log x is 1 over x. So when we do dy dx times x, we get beta 2 1 over x times x, which is indeed beta 2. So we see that beta 2 is equal to this expression. And this expression is approximately equal to the change in y divided by the percentage change in x. So that means that we can view beta 2 as approximately the increase in y when x changes by 1%. If we divide beta 2 by 100, because increasing x by 1% is the same thing as making this equal to 0.01. In the linear regression model, we have the expected value of yi given xi is beta 1 plus beta 2 log of xi, at least if the x variable is exogenous. So that means that in this linear regression model, where we have logged our x variable, we have a partial expected value of y don't need the I here, given partial x is, and that multiplied by x, that is beta 2. We can generalize this result, of course, to several explanatory variables. So we have the following results for when we log the x variables. So if one or more explanatory variables are logged, then the corresponding beta parameters of the logged explanatory variables must be interpreted like this. If we look at the second result first, the partial derivative of the expected value y given x with respect to the jth variable, and then multiply that by the jth variable. That's the interpretation for those x variables that are logged. And remember, the interpretation of this result is if x increases by 1%, then the expected value of y increases by approximately the beta divided by 100. For the first result, we can immediately see from this equation here that if I differentiate e y given x with respect to log xi with respect to this variable, then that's beta 2. So that's another interpretation which is equally valid. The increase in the expected y when log xi increases by 1 unit approximately. You can mix these guys, so you can do ordinary least squares, do final, you can do log SATM and perhaps log SATV, but skipping the log on the GPA. That's perfectly valid, as long as you remember how to interpret the parameters. So in this case, since we have log SATM, this number must be interpreted as follows. If SATM increases by 1%, the expected final results increases by 0.32 points. Same interpretation with the SATV, while for the GPA, it's not logged, so you have to interpret it in units. If GPA increases by if GPA increases by 1 unit, the final result increases by 0.37 points. Finally, this model is sometimes called the linear log model because we have linear things on this side and log on that side. So we basically have 4 types of models. We have the most common one, the log-log model, which looks like this. Log yi is beta 1 plus beta 2 log xi plus epsilon I, and of course you can have more explanatory variables. We have the log linear model, which looks like this. Beta 1 plus beta 2 xi plus epsilon I. We have the lin log model, which is yi is beta 1 plus beta 2 log xi plus epsilon I. And we can even add, just for fun, the lin model. That would be a model which is a linear regression model that's also linear in data. For the interpretation, it's pretty straightforward to remember. Just remember that whenever you log a variable, the interpretation of the parameter beta needs to be changed to percentage instead of units. So for example, in the log-log model, beta 2, since we have both logged y and logged x's, must be interpreted as the increase in y in percentages if x increases by 1%. In the log linear model, only y is logged and not x, so beta 2 is the increase in x, the percentage increase in y if x increases by 1 unit. And if you want this interpretation to be in percent, such as 3% for example, you have to multiply beta 2 by 100. The lin log model, now we have a log on the x but not on the y, so the interpretation is the increase. If we increase, sorry, it is interpreted as the unit increase in y if x increases by 1%. And since we increase by 1%, that's 0.01. So to get the correct interpretation in this case, you have to divide beta 2 by 100. And of course, you have the linear model when you don't have any logs, so that reverts to the standard one. Beta 2 then measures the unit increase in yi if xi increases by 1 unit.